Welcome to Calc 3. This is section 13.4, center of mass. This is going over an example of center of mass. So let's suppose that you're given the region as a disk with radius 2 centered at the origin, and delta, the density function, is given as x plus y plus 4, and we're asked to find the center of mass. Recall our center of mass is given in where the mass of the lamina plate is the double integral of the region of the density function. The moment with respect to x is the double integral over y times the density function of the region, and the moment with respect to y is x times the density function, where we're taking the double integral of that. And then x bar, y bar, the center of mass, is given by the moments divided by the mass. So one thing to know is that when we're looking at a disk, polar coordinates may be helpful here. So recall that polar coordinates, we have x is equal to r cosine theta, y is equal to r sine theta, x squared plus y squared equals r squared, and our Jacobian is equal to r dr d theta. So if we make a coordinate transform from Cartesian to polar coordinates, we need to make sure to include the Jacobian. So in our disk of radius 2, centered at the origin, we have that r, our region, is, or radius goes from 0 to 2, and theta goes from 0 to 2 pi if we're covering the entire disk. So we can convert our double integral for our mass from our region for a density function x plus y plus 4 dA. We can convert this to the integral from 0 to 2 pi, the integral from 0 to 2 of r cosine theta, that's our x, plus r sine theta, that's our y, plus 4, and then tack on our Jacobian r dr d theta. So when we have this function, again, this is our x and this is our y that we substitute in. Our inner function here goes from 0 to 2, distributing through the r, we get r squared cosine of theta plus r squared sine of theta plus 4r dr. So our inner function is 1/3 r cubed, factoring out the cosine theta plus the sine theta, plus 2r squared, evaluated from 0 to 2. This gives us 8/3 cosine theta plus sine theta plus 8. So, and notice that when we evaluate at the zero terms drop off. Sorry, the bracket goes around this piece here. So now our outer function, we go from 0 to 2 pi, and we have 8/3 cosine of theta plus sine theta, keeping track of our parentheses, plus 8 d theta. These are easy functions to integrate, so we get 8/3 negative 8/3 sine of theta minus 8/3 cosine of theta plus 8 theta, evaluated from 0 to 2 pi. So the first term will drop off at both 2 pi and 0. So we get minus 8/3 times 1 plus 16 pi. And then we subtract off again at 0. Sine of 0 is 0. Cosine of 0 is 1. So we get minus 8/3 here times 1 plus 0. And these two 8/3 cancel, and we're left with 16 pi as our mass of this disk. So now when we look at our moments about the x-axis, from 0 to 2 pi. And notice this is a symmetric disk, as well as the function itself is symmetric. The density function is symmetric, x plus y plus 4. So when we calculate the moment for x, it should be the same for the moment for y. So we'll just calculate the moment for x, and I'll leave it to you to verify it's the same for the moment for y. So the moment about the x-axis, 0 to 2 pi, 0 to 2. So we have our our y times x plus y plus 4. This is our r d theta. I do have coordinate systems that are mixed up here just for visual reference of the two moments. So let's convert it all to the same system. So we have 0 to 2 pi, 0 to 2 of r sine theta times r cosine theta plus r sine theta plus 4 times r dr d theta. Cleaning this up a little bit gives us our inner function as the integral from 0 to 2 of r cubed cosine theta sine theta plus r cubed sine squared theta plus 4r squared sine theta dr. So with this, we can integrate this, and our inner function then becomes 1/4 r to the 4th sine theta cosine theta plus sine squared theta plus 4/3, clean that up, 4/3 r cubed sine of theta evaluated from 0 to 2. So our inner function becomes, after some manipulation, 4 times the quantity sine theta cosine theta plus sine squared theta plus 32/3 sine theta. So then our outer function becomes 0 to 2 pi of 4 times the quantity sine theta cosine theta plus sine squared theta plus 32/3 sine of theta d theta. So now we just need to integrate this outer function. So when we're integrating this outer function, we've got 3 pieces here. So let's break up this outer function into 3 pieces. We have 0 to 2 pi of 4 sine of theta cosine of theta d theta plus 0 to 2 pi of 4 sine squared of theta d theta plus 0 to 2 pi of 32/3 sine theta d theta. Some of these terms are easier to integrate than others. For example, the first term is a u substitution. So if we let u equal sine of theta, du is equal to cosine theta d theta. So we have the integral of 4u du. So then we get 2u squared as our antiderivative. So this gives us 2 times sine squared of theta evaluated from 0 to 2 pi. And our third piece is we have, it's a nice integral, so we have negative 32/3 cosine of theta evaluated from 0 to 2 pi. So those two integrals are nice and easy to evaluate. Now the middle integral, we can use the trig identity, where we have sine squared of theta is equal to 1/2 quantity 1 minus cosine of 2 theta. This is a double angle identity. So then 4 sine squared of theta is equal to 2 minus 2 cosine of 2 theta. And then we could do a u substitution on that to solve for that. And so we get that the integral then becomes 2 theta minus cosine, 2 theta minus sine of 2 theta, evaluated from 0 to 2 pi. So now that we have all these pieces, we can solve our integral. So sine squared, or sine at 2 pi is 0, so the first term is 0, plus, so we have 0 minus 0, evaluating the fundamental theorem of calculus on the first term. Then we have 4 pi minus sine of 4 pi is 0. And so we have 0. So we have 4 pi for the second term. And then minus 32. So cosine of 2 pi is 1. Minus, and then minus 32. Cosine of 0 is 1. So these will cancel out, leaving us with 0. So our total answer for this integral is 4 pi. So that means we were calculating the moment about the x-axis, so y bar, which is the moment about the x-axis over the mass, is 4 pi over 16 pi, which gives us 1/4. And since this is a symmetric disk, and our function, our density function is symmetric, by symmetry, and you can check this as well, x bar is equal to y bar, so that means our center of mass is equal to 1/4, 1/4. If you have questions, as always, feel free to email me. And our next topic will be on surface area.